Now, if we write this in like a set notation, we'd write it like this. 0, 1, -1, 2, -2, and it goes forever. So I go dot, dot, dot this way, and this way, dot, dot, dot. That's the way we write it as a set of numbers. Does that make sense, that notation?
Yeah.
And then if you really wanted to get into it, there's another symbol for it, which is, again, used more as you move on and do more math, and that is a double struck capital Z. So y'all have seen this before, right? That means all real numbers. That's that's the number line, every number, all the fractions, all the decimals, everything in there, right? If you just want to talk about the integers, you put a double struck Z like this. And then it's understood that that means integers. We won't use that in here, but I'm just showing it to you. Okay, so what does this function do? You plug in some value x, right? Doesn't matter what the x is. And what this function does is it gives you the greatest integer that is less than or equal to the number you're plugging in. And remember, when we say greatest, when you're looking at a number line, any number to the right of another number is greater. So you would say 0 is greater than -1 here, right? You'd say -1 is greater than -2. You'd say 2 is greater than -1, right? So numbers to the right are greater than the ones to the left. All right, so let's try this. I'll start with an example. Hopefully this will make sense. Let's do a decimal, because those are usually the easiest ones to start with. Okay, 4.5. So what I want to do is I want to think about, like on this number line, let me do my number line again. If I come out here, here's 4, here's 5. I'm trying to plug in 4.5, right? Right here, into this function. And what this function should do is it should spit out the greatest integer that is less than or equal to the number I just plugged in. So if I'm plugging this in, what's the greatest integer less than or equal to that? 4, right? 4. That is the biggest number, sorry, that is the biggest integer that's less than or equal to that number, right? 4.5. So this should spit out 4. Okay? It's that simple, yes. Okay, what about this? What if I tried to plug in 4.2? What would I get? Still 4, right? 4.2 is where? Like somewhere in here? That would spit out 4 as well. How about 4.99? Just 99, not 999 repeated. Just 4.99. So I'm almost here, right? I'm really close to 5. What's the greatest integer less than or equal to that? Still 4, right? So see, this function isn't like rounding. It's not doing our normal rounding, right? It's actually rounding down, right? It's rounding down. No matter what, it rounds down. You see that? And then, let's see, what about f of 4? So now we're actually plugging in 4, right? And 3 is over here. We're plugging in 4. What is the greatest integer less than or equal to 4? 4 itself. Do you see that? 4 itself is less than or equal to 4. So when we plug in 4, we get 4. Understand?
I think I'm starting to
Get it?
I'm more confused with how it's going to be computers.
Yeah, that's a different story. But let's make sure we understand it first. All right? Okay, got it? All right. With this idea of f of 4 is 4, what's f of 5? 5. What's f of 6? 6. What's f of 7? 7. Right? So if you plug in an integer, it spits out that integer, right? That's what it does. The place that this function is interesting is when you plug in things in between integers. That's when things get interesting. All right, got a basic idea so far?
Same thing for negatives.
Yeah, now let's look at some negatives. What if we plug in -3? Well, that's an integer, right? So it should just spit out -3. What if we plug in -4? It should spit out -4. What if we plug in 0? Is 0 an integer? Yeah, 0, right? So if you plug in an integer, it spits out the integer. Now let's do a hard one. -4.5. So instead of that, negative 4.5. So I'm going to draw a number line. Here's negative 4. Here's negative what? 3. Here's negative 5. I'm plugging in negative 4.5, which is there, right? What is the greatest integer less than or equal to that number? Negative 5. Negative 5, because less than means to the left. So this is actually negative 5. A lot of students will say, oh, that's negative 4. No, it's not negative 4. It's negative 5, because negative 5 is less than negative 4.5. Right. Make sense? Okay, now, I'm ready to try and graph this now, okay? So to graph this, see what it looks like here. Let's start with the easy stuff. Let's plug in integers first. If I plug in 0, I get what? 0. If I plug in 1, I get 1. When I plug in 2, I get 2. When I plug in 3, I get 3, right? What is that looking like so far? Like the identity, kind of, right? Isn't that looking kind of like the identity? What happens if I plug in negative 1? Get negative 1, right? What happens if I plug in negative 2? I get negative 2. Right? All the integers spit out just whatever goes in is what comes out. Yeah? Let's go one more. Maybe two more over here. Let's go 4. We're up here at 4. And if we go 5, we're up here at 5. All right, what happened when we plugged in 4.5? That was the first one I gave you, right? What happened when we plugged in 4.5 right here? It spit out 4, right? So where's 4 here? 1, here's 3, here's 4, and here's 5. So when we plugged in 4.5, we got 4. What about when we plugged in 4.2? We got 4. What about when we plugged in 4.99? We got 4, right? And wouldn't any number in between here and here give us 4? So that means it's going to be a little line segment, just like that. And then what about at 5? At 5 it jumps, doesn't it? But because I can pick like 4.99, 4.999, 4.9999, I'm going to put an open circle underneath this to let you know that I can do any number all the way up to when I get to 5. And then once I get to 5, I jump up to 5. What would happen at 3.5? If I plug in 3.5, it would spit out 3. How about 3.2? 3. 3.99? 3, right? Same thing. Do y'all see we're going to start to get a little pattern develop here? What does that look like? Looks like a staircase. We call this function a step function. This is an example of what's called a step function. Because it looks like steps, doesn't it? Now, that's what the graph looks like, okay? That's what it looks like. Any questions on this? Let's talk about domain. What's domain of this function? All reals. You can plug any number you want into this, right? You got picture, picture. Even though these are open circles, remember at 2 you have a value. At 3 you do have a value. At 4 you have a value. So we have the functions defined everywhere, all right? The range is a tricky one. What's the range? All the integers, right? Think about the outputs. You're only going to get the integers as outputs, right? 0, 1, 2, 3, 4. You don't have anything in between, do you? Right? So how do we say the range is the integers? We could just use z, or we could write like this, dot, 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 -3, -2, -1, 0, 1, 2, 3, dot, 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 or say, screw all that, just do like that. That's your integers. Sorry, that's sloppy. Here's a tricky question. Is this function ever increasing? No, it's not. You're always what? Constant. And then when you go up to the next level, right, you're constant. Next level, constant. Next level, constant. Next level, constant. So it's never going up, even though it looks like the steps are going up. You never actually have upward motion like that. And it's never going down, right? So it's always constant. Yeah, that's good. Now, in computer science, all right, in computer science, this function actually has a different name. It's not called the greatest integer function in computer science. In computer science, it is called the floor function. It's called the floor function. And the idea is that no matter what you plug in, it drops it down to the floor. So if I plug in 4.5, right, 4.5 is up here. That's where it should be. I drop it down to 4. If I plug in 3.5, I drop it down to 3, right? Plug in 2.5, drops it down to 2. So every number you plug in, it drops down to the next integer below it, right? The floor. There's another function in computer science that the book does not mention. Does anyone know what it's called? It's the opposite of this one. It's not called the floor, it's called the ceiling function. And what do you think that function does? It takes you up to the integer above it instead of the integer below.
So it's greatest integer.
It would be the least integer less than or equal. Wait.
How would you graph that?
Yeah, what would it look like? I'll do it in red. At 4.5, where would you be? So instead of being, at 4.5, instead of being here, right, we drop down for the floor. Where would we go for the ceiling function? Up. We go up to there. Okay? And then it would go everything like that until you get back here, and then that one would be below. It's more computer science, but it's step functions we need to be clear on in calculus. Just generally, what are step functions? But the floor and ceiling are used in computer science because a lot of times you have answers and you have rounding, or you have some rounding, and you know what? You don't want the decimals, so you're either going to drop everything down to the floor or you're going to take it up to the ceiling. One or the other. Just depends on the application. Okay, that's it. This is the only one. We're not going to do ceiling. All right, there's the floor. All right, those are the, let me double check. Those are the toolbox functions. That's all of them according to your textbook. Those are the ones you need to know. Right? So we have these, and then how many more did we do today? How many is it total? 1, 2, 3. So 9 total? I think it's 9 total. You should know what they look like. Well, once you take pre-cal, you'll have more to add to your toolbox, right? So you take pre-cal, we'll add the sine function, the cosine function, the tangent function. And so we just keep adding. Also, there's going to be, later on this class, exponential functions, log functions. So there are more to add to this. But for right now where we are, this is it. All right, now, we're going to do an example of a piecewise function. I thought you said it was, yeah, okay. You did say it was I before E. All right, we're right. So I want us to take a look at this. I'm going to erase this. I've got to sneeze. Do you know why people bless people when they sneeze?
Why?
Do you know why historically?
Greece, they thought it was involuntary. They thought the gods were telling them something.
I haven't heard that one. That might be true. I've heard that, like back in the old days, you're sneezing, you're sick, you're probably dying because medicine wasn't the way it is now, right? So like you probably had something bad, like probably won't be here next week. Bless you. You know?
There could be like 10 different reasons.
Yeah, I'm sure there's a bunch of different
There's a
reasons.
lot of people that never met each other that's had it for different reasons.
Yeah. All right, here we go. All right, this is it. This is a piecewise function. And what we want to do here is answer questions A, B, C, D, and E. All right? All right, so here's the function. There are two pieces, right? There are two pieces to this function. And we are going to look here whenever x is less than 0. And we are going to look here whenever the x we're plugging in is greater than or equal to 0. So let's start off with part A. Let's find f of negative 4. So if we plug in negative 4, are we going to be using the top or bottom function?
Top.
Top one, right? If you're plugging in negative 4 is less than 0, so you plug negative 4 in right there. And when you replace x with negative 4, you get positive 8. Two negatives multiplied to be positive. That pretty straightforward?
Yeah.
No? Did I hear no? What about 0? If we plug in 0, top or bottom? Is 0 less than 0? No. Is 0 greater than or equal to 0? Yes. Right? So when I plug in 0, I'm going to be working in this one. Square root of 0 is 0. F of 4. Okay. Is 4 less than 4? No. Is 4 greater than or equal to 4? I mean, sorry, did I just say that? I did say it. Is 4 less than 0? No. Is 4 greater than or equal to 0? Yes. So we plug 4 into this. Square root of 4 is 2. All right? So that's how you evaluate a piecewise function. You check to see the number you're plugging in. That will tell you where you're falling into, either the top or bottom. And then from that, you plug in. Piecewise functions can have more than 2 pieces. You can have a piecewise function with 3 pieces, or 4, or 5, or 10. Doesn't matter. Does anyone here pay their own water bill? Yeah. So if you use water, if you use saws, they have a tiered stepwise function to determine your pay, how much you owe. If you use a certain number of gallons, you get charged a certain amount per gallon. So like if you only use 2,000 gallons a month, it's very cheap. It's only a few cents a gallon. But when you go to the next tier, and now you're using, let's say, between 2,000 and 4,000 gallons, then your rate goes up. And if you use a lot of water, the rate gets crazy, like real crazy. Gets out of hand. So that's the way they kind of like penalize you for using too much water. It's a piecewise function. All right, so now part B, find the domain. Okay, so when we think about domain, what we want to do is look at this and we want to make sure that we are defined for all, x's. Is this function defined whenever x is to the left of 0? Yes, right? This function, we can plug any negative, these are negative numbers. Can we plug negative numbers in here and have any issue? Are there any issues if we plug negatives in here? No. So this should be good so long as we're to the left of 0. What about from 0, positive, this means positive values of x or 0? That means to the right of 0. Is this defined for every number from 0 on to the right? Yes? Even though we know it's not defined for negatives, but we're not even looking at negatives for this, are we? So this should be defined everywhere here for that. So this function is defined where? Everywhere, right? Negative infinity to infinity. The function is defined everywhere. You can plug any number you want into this function. All right, intercepts. And we haven't talked about intercepts in a while. Let's talk about first x-intercepts. This is going to be a reoccurring theme in this class. How do we find the x-intercepts for any function, no matter what function we're ever looking at? You need to remember what to do. You take the function and set it equal to 0. You ask yourself, when is the function 0? Well, this is tricky, right? Because you're setting the function equal to 0, but the function is 2 different pieces, isn't it? So we have to look at two different scenarios. First, we have to look at, is negative 2x ever equal to 0? And then the other one is the square root of x ever equal to 0? We have to look at both pieces and ask ourselves, are these ever 0? So solve this equation. Is this ever 0? When x is what? When x is 0, right? That appears to be an answer, yes? But I'm going to throw it away. Why? Why am I going to throw this answer out?
Because it'll never happen.
This is saying for
Zero by zero.
this to be 0, right? For this to be 0, we need to plug in 0, don't we, for x? But when we're looking at this function, are we allowed to plug 0 in? No, we're not. You see, that's why I'm throwing it out. Because even though 0 would make this, plugging in 0 to this would make it 0, 0 is not in the domain of this piece. You see? So I throw it away. What about this one? What value of x do you plug in to get 0? 0. Now, can I keep that or throw it away? Keep it, because to solve this equation equal to 0, we're going to be here. Can x ever be 0 here? Yes. So this will be my x-intercept. All right, how do you find the y-intercept of a function? This is the easier one. Yeah, you replace 0, you plug 0 into the function. That's it. You just plug 0 in. And when we plug 0 in, didn't we do that earlier? Part A, right? When you plug 0 in, you can only be on the bottom piece. And so when you plug 0 in, you get 0. That's your y-intercept. Questions, comments, concerns, complaints, gripes? We're going to graph it now, all right? We're going to graph the function. And to graph this function, you need to know your toolbox functions now, all right? This is where it comes into play. So the way I'm going to graph this is as follows. Where do our two pieces come together? At what x value do these two pieces, these two different functions come together? At 0, right? At 0 is where they come together. So I'm not going to draw, this is like an imaginary line, okay? This is just so I can remember. This is like a reference for myself. That red line is at x equals 0. I know that to the left of this line, it's going to be that graph, right? And to the right of this line, it's going to be this graph. Make sense? Let's start with the one I think is the easier one, square root of x. That's something everyone here should now know what it looks like. And so to graph this, I know what the square root of x looks like. I'm allowed to plug 0 in, so I know at 0 I am 0, and then it looks like this. Right? That's what the square root of x looks like from last class. And then the other piece that I'm going to graph is this. And this I know from college algebra. I mean, not college algebra, from previous math courses, right? This is negative 2x. This is your slope of your line. This is a linear graph. So your slope is negative 2, which means that it should pitch down like this. And here it's an open circle, but the blue dot fills it in anyway. I'm just kind of stressing again. It's open here because there's nothing underneath the inequality. That is the graph of this piecewise function. Okay? Domain. Oh, it doesn't. Oh, we already got domain, but you can see domain now, right? It's a lot easier to see it here. It's everything. And then what about range? 0 to infinity. Including 0, right? Including 0. All right, I'm going to move on to the next one. I have 10 minutes, about 10 minutes, so I'm going to try and get one more of these. Here's a piecewise function with 3 pieces. Before I do this one, we have not done a formal review of this, and I just want to make a quick review, because I'm assuming you know this. I'm assuming everyone here knows how to graph a line y equals mx plus b. I'm assuming you know how to do this.
Yes.
So just to be clear, if you were to have a line like negative 4x plus 3, and I asked you to graph that, what I expect that you would know is that this number right here represents your y-intercept, so you go up 1, 2, 3. You'd put a dot, and then to get to another point on the line, you would use the fact that this number is your slope. and that's -4, which we write as a fraction, -4/1, and that gives you your rise over run. So to get to another point, I go where? Down 1, 2, 3, 4, and then over 1 to the right 1. Draw a dot, draw a line, right? I'm assuming everyone here knows how to do that. If you don't, then there's a real quick reminder of how it's done. All right, here's the function that we want to draw now, this piecewise. 3 pieces, right? 3 pieces, 2x plus 1, that's a line. If -3 is less than or equal to x is less than 1, it's 2 if x is exactly 1, and it's x squared if x is greater than 1. Now, I'm not going to follow the directions here, okay? I'm going to just try and graph this right now. I'm going to see if I can graph it. So here's how I'd go about graphing this. I would find where I have something interesting happening. So I'm going to start with the first one. This first piece only happens between -3 and 1, right? So I go to the left, -3, and here's 1. And I'm going to imagine, like, again, this is kind of an imaginary line just to kind of keep, I'm going to break this picture into some pieces here. Pieces, piecewise function. Okay, at 1, we've got something happening, right? And then greater than 1, so to the right of 1. Does this function have anything going on to the left of -3? No, right? It's not defined over here. If I try and plug in -4, it doesn't work. This is what you were asking earlier, right? Is it what happens if you try and plug in a number and it doesn't fall into this, right? Then it would just be outside the domain, and therefore it would be undefined. So you cannot plug -4 into this. You can't plug in -10. All right, so here, now I'm going to try and graph it. So let me start out with this first piece. Right here. That is a line, right? And to graph that line, I'm going to use the method I just showed you. I would go, on the y-axis, I would go up what? 1, I would put a dot, right? And then from there, I would use the slope is -2/1, so that means I go down to the right 1, right? Let me go down to 1, 2, to the right 1, I'd be here, right? And now I draw a line through those, yes? Now I'm drawing it very lightly with a pencil. Very lightly, draw this. Right, it would go like that. And I'm going to stop right here. Why am I stopping right here? Because it's only to -3, right? So I'm going to put a dot there. Why am I putting a dot, not a hole? Because I have a bar here, right? That bar says that I actually have a dot there. Now, do I continue this line forever? No, where do I stop it? When I get here, right? Because it stops at 1. So when I'm going to erase that part of the line that I drew. And then here, should I put a solid dot or an open circle? Open. Because this is not defined at 1. You'll see that? This is supposed to be straight. Okay? That is the first piece graphed. That's the first piece. Any questions on that piece? Now I'm going to go to the second piece. If x is 1, I plug in 2. If x is 1, the output is 2. So if I plug in 1, here's 1, right? My output is 2. So up 1, 2, here's 2. So if I plug in 1, I get 2. I put a solid dot just like this, right? That takes care of this middle piece. Questions on that? Remember, this red line is not like a vertical asymptote. This is just so I can see my different sections of the graph. Okay, the next one. The next piece looks like x squared. And I know what x squared looks like, right? It looks like this. That's what x squared looks like. And so I would start drawing it like this. I need my graph to be somewhat decent. Remember when we plug 0 into that, we would get 0. If we plugged in 1, we'd get 1. It looks like this. And it does the same thing this way, right? However, I'm only going to draw it where? Greater than 1, right? So I only want to draw that from here over. So I would come back and I would erase the parts of the parabola that I don't need, right? And then right here, what would I put? A dot? Open circle. Open circle, why? There's no bar here, right? There's no bar underneath this. So I put an open circle here, and then the rest of it, let me exaggerate this a little bit. The rest of it is the parabola that goes like this. That's your piecewise function. Questions? Pardon me? Yeah, but that is the piecewise function.
So it doesn't go like the parabola, it doesn't go on the other side?
No, it doesn't, because remember, this parabola only exists when x is bigger than 1, right? So that parabola should only exist from 1 that way. I drew the whole thing just to help me kind of get my bearings on where things are, right? So this line, this blue piece only exists between here and here. That bar meant I put a dot. That no bar here, put an open circle, right? Here means when I plug in 1, it should spit out 2. Boom, there's the red dot. And then the green is, like I just said, to the right. Is this function continuous everywhere? Can I draw it without picking up my pencil? No, right? Remember we talked about continuous functions means you can draw it without picking up your pencil? This is not a continuous function.
Only from -3 to 1.
Yeah, between here and here it would be continuous, right? And then over here, this section, it would be continuous. But right here at 1, you have a problem with the continuity, right? Like you're drawing, and you have to pick up your pencil, put that, and then pick it up and go here. Okay. Y'all good?
Yeah.
What time is it? Almost. All right, so can we answer at least, what the domain of this is? Just by looking at the picture. Yeah, it starts at -3.
Infinity.
Do I get everything? Does every x value have some y output here?
Yes.
Yes, even at 1, right? At 1 we get 2. So we have a domain would be from -3 to infinity. What about the range? Range is a tricky one. The range is a little tricky.
So
It's like from